Okay. My name is Bruno da Silva, and I'm from Sidia. That's an institute of science and technology from Manaus in Brazil. That is the Samsung Institute here that we have, you know. And I am an R&D engineer from Samsung. So today we're going to present a lab study that we've done about it's a measurement study on 5G on NSA architecture over fading channel. Okay. Just to confirm, can you hear me? Can you hear me?
Yes, we can hear you. You can proceed.
Oh, okay. Thank you.
Yep, we can hear you. Yep.
Let's go. The 5G architecture that we call non-standalone, you know, it aims to advance with regard to throughput on 5G networks. In this kind of architecture, the LTE core is used, you know, like an anchor to connection of 5G. So I can improve my throughput that once was on LTE, now on LTE and NR, you know, so I can get better data rates. And to evaluation and, you know, the optimization of the system of 5G, it is very necessary to carry out practical studies, you know, on behavior on the system in different environment conditions. That's where I have to talk about the attenuations. You know, the signal travels through the air, and it takes a lot of some kind of attenuations. We call some of large scale fading, you know, that's the shadowing, and the small scale fading, that is for the multipath propagation. Just to show you and present the NSA architecture of 5G. It was standardized by the 3GPP, as we all know. And as I said, it connects both LTE and NR networks, where the LTE is the anchor of the system. All the signaling and the process is done on the 4G, you know, the 4G packet core that in this figure you can see the EPC, right? This is the core of the 4G. And as I said, it improves the total network coverage, you know, because now I have 2 cells, and then increase the data rate because of the addition of the 5G cell. And this kind of architecture is being the most deployed in the world for, you know, some saving time and reducing costs for the operators. Since the SA architecture that we call the pure 5G, it needs a completely different network core. It doesn't work with the EPC that we can see here. It needs a new core, and you know, this means costs for the operators. So the NSA architecture makes use of the standard network architecture 4G to make a smoothing in this transition from 5G from 4G to 5G. And in all communications, we have the thermal noise that in physics, in telecommunications, we used to model it like a WGN channel. And this noise, for thermal noise, it makes some kind of the decision making in the receiver difficult, because as you can see in the constellations in the figures, when we add noise to our signal in the traveling signal, we have a constellation more, you know, sparse. So this difficults the modulation, and we have more errors in our reception, which leads to a BLER, that's the block rate error rate, a high BLER rate. The faded channel also adds to the signal some uncertainties about its demodulation, you know, because the receiver receives multiple copies of the signal sent by the transmitter due to several reflective and diffracting objects. And these signals with relative time delays and different orientations about his arriving, it makes some zones of zero and some add signals. We aims to analyze how the MCS, how the modulation of a 5G system can affect its throughput rate in a channel with, at first, a WGN, and secondly, with a WGN and fading channel and fading, that makes more difficult the demodulation. So we, in this study, we aim to analyze this. For this, we consider these parameters, you know, for campaigns that we run out in our lab here in Manaus. And this is the most important parameters in our campaign. It's important to highlight the band, the NR band that we used, that was N78 with 100 megahertz. And the LTE band was the band 1, centered in 2.1 gigahertz. The LTE MCS was fixed in 44 QM. The resource blocks allocated to the user equipment was 273. The modulations that we analyzed was the 44 and the 256 QM modulations. With the transmission mode CISO, that is just one output and one input, you know, or it means just one antenna. And the faded profile that was chosen was a suburban fade profile to emulate a real scenario. Okay. This is the diagram of our setup in our lab. Obvious, it's very simplified, but we count with two MT 8000, you know, that emulates the cells, the NR cell, either LT cell. The duty, that is the user equipment and smartphone, and a fading server that introduces the fading effect on signal generated by the MTs. And all this stuff goes to a control PC where we have our interface that we can study the results of our campaign. So going to the results, we see these two tables. It's a comparison in the signal sent. Consider just the WGN on the left, and the signal sent transmitted. Consider WGN and fading. As we can see, and as we were expect, the signal with fading has a BLER index much higher than the signals, the transmission under just the WGN. Of course, when we add the fading effect, it makes the demodulation of our signal most difficult, most difficult for the reasons that I've shown you before. So in this table, we gotta resume about this. Consider both simulation for 64 QOM and 256 QOM. And we see that for a higher order modulation, the 256 QOM, we have worse results because in the constellation, the space between the symbols in a higher order modulation are less than a low order modulation. So it means that the errors is most probably to occur in this high order modulation like 256 QM, as we can see by the numbers of these tables. Looking through a graph, this is the variation of the SNR, the signal noise ratio, and the comparison with the throughput rate in percent. And we see that consider the 64 QM modulation in a low MCS, that means a lower order modulation with a little bit of bits add to help in the modulation, the coding bits. We see that almost time from 14 to 30 dB in the SNR level. We can see that we can have the 100% of the throughput, right? And this goes down since I have the MCSs higher. These two tables is the analysis, the comparison for 64 QM and 256 QM. And we see that, as I said, the high order modulation has a better, a worse result. My timing is running out of this. And this is the comparison, the comparison of the LWGN plus fading. Again, the high order modulation has a worse result as we expected, because it's more difficult to demodulate a higher order modulation, because the symbols are very together, let's say like that. This present work I'm to study some laboratory measurements taken in Sidia lab about the influence of modulation cut scheme over throughput of a 5G NSA network, considering theoretical scenario with effect of LWGN and further analysis in which effect of fading was added to the signal. And although generally a BLER of 10% or less is the target, certain conditions, certain scenarios, it can show good functionality under higher values. So this work is a base to understand how the MCS scheduling by the network to the OE can be a trigger, or can be one of the triggers, to see how the BLER of a system works. A new MCS allocation model must be developed to meet specific throughput demands according to each scenario that we have shown in this study, right? And for future works, other frequency bands in 5G, like at the FR2 band, will be studied in order to understand the behavior of the network on the fading and how strategies can be applied to optimize the system, such as the implementation of MIMO and proposal of some MCS allocation algorithms according to a specific application and specific BLER targets. So thank you, everyone. If you have any question, I have to say that it's a pleasure to me to share this information of our team with you.